It's okay. Hello. Yeah, I'm another day late on this. In the first four problems, I messed up two of them so bad that I had to take a little nap in order to figure out where I made a mistake, and it was a negative sign both times. I cannot emphasize enough how much being patient in writing what you're writing and being careful. Let's talk about this, and I'll show you where I made my mistakes. And oh, it was so frustrating. Today, what I meant to say was, hey, how you doing? Welcome to class. Today we're talking about section 7.3, multivariable linear systems. So the elimination method we had talked about last time, we're going to extend that because now we have three variables. A lot of times we'll have three equations. And the three equations in three variables is generally given to us in both or in all of x, y, z, and our constants over here. What we want to do is we want to follow a system. Notice that word system. We're being very specific about what we do in order to make a stair-step-like pattern right here where we have each term a leading x, down one step a leading y, down one step a leading z. Notice the coefficients of x, y, and z in the lead are always 1. That's going to be important. So this section we're going to learn how to take a system like this, rewrite it into a system like this so that we can solve it as we go back up the steps. Here we go. So this second system is said to be in row echelon form. It means that it has a stair-step pattern with leading coefficients of 1. After comparing the two systems, hopefully you could see that the second one is much easier to solve than the first one. I could look and say, hey, z is 2. If I know what z is, I can find y. If I know y and z, I can find x. Here, that's a shot in the dark. Two systems of equations are equivalent if they have the same solution set, and we use operations that take our first system using equivalent operations, equivalence manipulations, we arrive at the second one that's easier to solve. Wow, my goodness. To solve a system that is not in row echelon form, first convert it to an equivalent system that is in row echelon form by using the following operations. You'll notice this is very similar to the elimination method. It's just generalized, and we gave it a name. The name is Gaussian elimination. So the process Gaussian elimination is named after the German mathematician Carl Friedrich Gauss. And if you look up a picture of Carl Friedrich Gauss and you look up a picture of, quote, the Royal Ugly Dudes from Bill and Ted's Excellent Adventure, that's where they got the image from the Royal Ugly Dudes, I swear. All right, but Gauss is one of the biggest mathematicians ever, and he was from the 1800s, and he gave us a lot of good things, and this is just one of many. Operations that produce equivalent systems. You'll notice we did something exactly like this in the elimination video that I sent you yesterday. Each of the following row operations on a system of linear equations produces an equivalent system of linear equations. So we could interchange any two equations. What was equation 1 could be equation 3. Throw up equation 2 into equation 1. You could put them wherever you want as long as you take the whole equation and move it. We can multiply one of the equations by a non-zero constant, right? We did that in the elimination method. And we could add a multiple of one of the equations to another equation to replace the latter equation. I'm going to show you this one a lot, and that's exactly what we did, right? We multiplied our equations appropriately, so we had the same coefficient differing by a sign, so when we add them together, the variable is eliminated. Same thing here, only in a very precise process. All right, this is would be where I take a drink in class, so I went ahead and did that for you. Okay, here we go. To solve the system given by x plus y plus z equals 6, 2x minus y plus z equals 3, and 3x minus z equals 0, the first thing we always want to do is get a 1x in the upper left corner. We have that, so it's all good. I'm going to change this to a yellow so that when I draw, it's different than anything that I've put on here before. All right, so we have a 1x, all is well. Now we want to use this equation and eliminate all the x's below it. So you'll notice here we have a 2x. Well, I can multiply. Wow, I didn't do this very well at all. I can multiply -2 times row 1 and add it to row 2 to get a new row 2. So I did -2 times x, y, z, and 6. That's -2x, -2y, -2z equals -12. Add it to... What is this? There must be a 2 here that I forgot to write. Oh my goodness, good thing I wrote the notes and then recorded them. There's a 2x here, minus y plus z equals 3. 2x minus y plus z equals 3. When I add them together, the 2x's are eliminated. Minus 3y minus z and a -9. That's the one I missed, by the way, and it ruined everything. To eliminate the x here, right, I eliminated my 2x, now I need to eliminate my 3x. I'm going to multiply my first equation by a -3, and that's why we make it a 1x in the upper left-hand column. What do I add to 2x? A -2x, so I know to multiply by -2. What do I add to 3x to eliminate it? -3x, so I know exactly what to multiply by to get my new rows each time. I'll multiply first row by -3. -3x minus 3y minus 3z equals -18. Add it to row 3. 3x minus z equals 0. Notice everything's lined up. When I add straight down, the x's are eliminated. I'll have -3y minus 4z equals -18, and this is my new row 3. Here's my new matrix, my second matrix. So it uses my original top, x plus y plus z equals 6, and then my new row 2, and my new row 3, where my x's are eliminated. All right, so we've started that step pattern. We're great with x's. Our next step, step 3. It looks like not all my ink stayed, and that happens sometimes. Get a 1y in the second equation, second term. So I want this to be a 1y. So I am going to multiply by a -1/3 this the row 2. Right? We can multiply any row by a non-zero number and replace it. So I'm going to divide by a -3 everywhere. When I do so, I'll get a y plus 1/3 z equals 3. I replace that here. All right, my new equation 2, y plus 1/3 z equals 3. And now I want to eliminate all the y's below it. In order to eliminate a -3y, I'll multiply by 3. I'll use the y, the one we just got a coefficient of 1, in order to eliminate the y below it. So 3 times row 2 added to row 3 is my new row 3. Let me see, 3 times row 2 is a plus sign right here. 3y plus z equals 9. Original row 3, -3y minus 4z equals -18. When I add these two together, I end up with a -3z equals 9, new row 3. Okay, so from the black one, I got a new matrix. Now I have an x, nothing below it. I have my 1y, no y's below it. My next goal is to get a 1z in the third equation, third column. So I'm going to divide by a -3, right? -3 divided by both sides. I'll get z equals 3. That's my final third equation. We have our stair-step pattern. And all we did was, in order, get a 1x, use that equation, eliminate all the x's below. Get a 1y in the second equation, use that equation, eliminate all the y's below. Get a 1z in the third equation. If we had more equations, we'd use that to eliminate all the z's below it. So this says, now that we have z equals 3, to finish, solve your way up the steps. If z equals 3 and y plus 1/3 z equals 3, I'll replace the z with a 3. And 1/3 of 3 is 1. Y plus 1 equals 3, so y must be 2. Now I know z and y. I could go to my top equation. X plus y plus z equals 6. I know y is 2, z is 3. So that's x plus 5 equals 6. Subtract 5 from both sides and we'll get x equals 1. I do encourage you to check these. Hit pause. You can check them in the original equations. Answers of 1, 2, and 3. But I did check them because I messed up on this problem and it took me about an hour and a half to figure it out. So I guarantee this one. All right, let's move on to the next problem. Same thing every time. Make the coefficient of the first equation, the first variable 1, use that, eliminate all of the x's below. Second equation, second variable, eliminate. Third equation, third variable, eliminate. Here we go. Our system is x minus 2y plus 3z equals 9, and minus x plus 3y equals negative 4. With a final equation of 2x minus 5y plus 5z equals 17. You'll find a lot of times in these classroom math that we'll always have a 1x at the top. We might mix it up on you, but it's almost always just a switch in order to get that. So we're good there. What we need to do now is eliminate all x's below that. So I have a 1x. And I want to eliminate a minus x, I can just add the two equations together, row 1 and row 2. When I do, right, I didn't multiply row 1 by anything. I took row 1 as it was, row 2 as it was, and I add them straight down. I'll get y plus 3z equals 5 as my new row 2. To eliminate this 2x, I will multiply by a negative 2 times the first row, add it to the third row to get a new row 3. I write instructions to myself so I remember what I did each time so that I could go back, like now, and explain it to somebody if I need to, or explain it to myself so I can figure out my error. After multiplying the first row by negative 2, add it to the third row, I'll get minus y minus z equals negative 1. So I have a new matrix. These matrices are all equivalent. I've used row operations that allow me to replace each equation with a new equivalent equation, but in our desired form. No x's below. So now I need a leading 1y, my second equation. It's already there. I'll use it to eliminate all the y's below. Hey, look, I can just add my equations together to eliminate y. Add them together. My new row 3 will be 2z equals 4. Fantastic. I have stair steps almost. I need to get this to be a 1. So my leading 1z, I'm going to multiply by half or divide by 2. And I have the stairs that I can now work my way back up. When z equals 2, y plus 3z equals 5. So that's y plus 6 equals 5. Y equals negative 1. If x minus 2y plus 3z equals 9, I can replace my y of negative 1, my z of 2, and I'll find that x plus 8 equals 9 or x equals 1. Checking all three original equations, make sure the answer pops up, or make sure the answer works in all three. Notice that sometimes the ones come very easily and the elimination kind of flows. Always the same thing. Make a 1 for the x, use it, eliminate all the x's below. Make a 1 for the first y, eliminate all the y's below. Never a choice on what to do next. It's always given to you in a procedure. It's a system. Okay, so what kind of solutions can we have with these linear systems where we're talking about 3 or more variables? For a system of linear equations, remember linear means no exponents other than 1 on the variables. No matter how many variables you have, exactly one of the following is true. You have exactly one solution, and you'll end up with z equals a number. You could back substitute up the steps. Or there are infinite many solutions. Just like last time, you'll find an equation that gives you 0 equals 0. always true. We'll talk about how to deal with that. And there's no solution. If you get a nonsense equation like 0 equals 3 or 0 equals negative 17, then we know there's no solution and we can stop trying to solve. So those probably are going to pop up in our next examples. Problem 3. Solve the system x minus 3y plus z equals 1, 2x minus y minus 2z equals 2, and x plus 2y minus 3z equals negative 1. We already have a 1x in the upper left-hand corner, so we'll use it to eliminate the x's below. I'll multiply row 1 by a negative 2 and add it to row 2 to get the second equation, x is eliminated. And I'll multiply row 1 by a negative 1 and add it to row 3 to get my new row 3. Okay, I'll be honest, I had to pause because my mouth was so dry. I thought it was probably bothering you. I'm better now. And I know that I said we were going to multiply and add. So that's exactly what we did. As we get our new row 2 and our new row 3, I noticed something a little funky here. 5y minus 4z is 0. 5y minus 4z is negative 2. Put a note there. If you noticed that was a little funky, you're right. Let's see what's going to happen. So we have eliminated all of our x's. We have our top stair. Now this 5y minus 4z, I need to make a 1y. I'll divide by 5 or multiply by 1/5, however you want to think of it. And so my new row 2 will be y minus 4/5 z equals 0. Cool. All right, there we are. But when I use this y minus 4/5 z equals 0 to eliminate all the y's below, right? I have a y and I have a 5y. So I'll need to multiply by a negative 5. Negative 5 times y, negative 5 times a negative 4/5 z, and negative 5 times 0. Add it to our row 3, and we get a nonsense equation. New row 3 is now 0 equals negative 2, and we know that's not right. As soon as we arrive at the nonsense third equation, we know this system has no solution. All right, so it could pop up as we're going along here, just like it did with the elimination method when we talked about it last time. Okay, what do? We just call it no solution. We're like, okay, great math. That was fun. Moving on. So problem 4. Oh, I already showed the answer down here. This is going to be a dependent system. In fact, all the rest of our answers will be a dependent system, so we're going to talk about this at length. So this system is ugly. I would rather not read it off. We could see that we do have this 1x in the upper left. We'll multiply the top equation by a negative 2, so that when we add it to the second equation, we could eliminate our x's. And then we'll multiply this top equation by a negative 3, so that when we add it to the third equation, we can cancel out the x. And when we do so, we find this was the other problem that I had to take a nap after. I had to just sit for a minute. It took another hour for me to figure out the error in this one. I tell you guys, I would rather just be in class. We could find the errors quicker if you're watching me. Okay. Minus 3y plus 15z equals 21. And 3y minus 15z equals a negative 21. Next, I want to make a 1y. So I will multiply by a negative 1/3 or divide everything by a negative 3. My new second equation is y minus 5z equals negative 7. I want to eliminate this y, the 3y, so I'll multiply my new row 2 by a negative 3. And it returns us exactly to where we were. Yes, I realize that. This step seems a little silly sometimes, but we have to do it. It's a system. And even though the system's a little wonky sometimes, the system never fails us. If we always do it in this order, we will always return equivalent systems. And when we do this, we notice, hey, these are the same equation. We're going to get 0 equals 0. So in our stair steps, we have something that's always true. Step 5 asks us to make a 1z, but we have an always true equation instead. For 3 variables, how we go about doing this is we'll let z equal z. Okay, just set z equals z. And use the steps to find x and y in terms of z. So if z is just z, the variable, then y minus 5z equals negative 7. I add 5z to both sides, and I find that y equals 5z minus 7. My top equation is x plus 2y minus 7z equals negative 4. X plus 2y minus 7z equals negative 4. I know that z is z, and y is 5z minus 7, so let me make that substitution. I'll simplify, distribute my 2. I combined my z values, the 10z and the minus 7, to give me a positive 3z. X minus 14 plus 3z equals negative 4. When I add 14 and subtract 3z from both sides, I find that x equals 10 minus 3z. So my solution, x, y, z, is 10 minus 3z, 5z minus 2, when z is z. And this is a dependent system. So you give me any z, I can tell you the x and the y that go with it, and now we have an answer. All right, 2 more problems. So far, each of the system of linear equations we've looked at has been square. The number of equations is equal to the number of variables. A non-square system is when the number of equations is different than the number of variables. This is very important. A system of linear equations cannot have a unique solution unless there are at least as many equations as there are variables in the system. Okay? If there are 3 variables, there has to be at least 3 equations for us to get a unique solution. Number 5, x minus 2y plus z equals 2. 2x minus y minus z equals 1. When I see 3 variables and only 2 equations, I know this is dependent. So I'm still going to use my stair-step idea. I'll get a 1x in the upper left-hand column. I'll use that 1x to eliminate the 2x below it. As I do over here, writing instructions for myself. My new row 2 is 3y minus 3z equals negative 3. So now I want to make a 1y. To do that, I'll divide everything by 3. I frequently call it multiplying by 1/3 because I like to multiply by rows instead of divide. Division makes things weird. If we always refer to it as multiplying, even multiplying with fractions, things stay less weird. So when I divide by 3 here, I'll end up with y minus z equals negative 1, and I have all of the stair-step that I can. In order to solve this, we'll set z equal to z. And then if y minus z equals negative 1, y equals z minus 1. My dogs want to say hi again. And if x minus 2y plus z equals 2, then I can substitute the z minus 1 for y. Solve. This one drove me nuts. Everything is a 2 or a z, it seems. My z's are crossed, and you can see why. The 2's and the z's look identical. But we have finally break it down to x is the same as z. And I encourage you to work through this. Hit pause. And then I'll come back whenever you're ready to unmute it. If x is z, y is z minus 1, and z is z, we have our solution. This last one probably could have used some more space, and I tried to do the best I could to put it on here, but I think my green got away from me and it ruined everything. Finally, we need a step to make a 1x up in that top left-hand side. So how do I do that? I divide by 2. Divide every single term in this equation by 2. We'll have x plus 3 halves y plus 3 halves z equals 7 halves. Now I want to use this x to eliminate all x's below it. So I will multiply negative 4 times row 1, add it to row 2. When I do, I end up with 12y plus 9z equals 30. I put it here. And I need to make a 1y. So then I'll divide everything by 12. And 9 over 12 is 3/4. 30 over 12 is 10 over 4, which is 5 over 2. And then if z is z, I can find y, and I can find my x value as well. Always check in the original, make sure it makes everything work out. This is Gaussian elimination, and we're going to come back to it in chapter 8. But the next lecture, which I admit is still a day late, and I'm still going to get it to you, the next lecture is on partial fraction decomposition, and it almost makes me sad that I wasn't, no, it actually does make me sad that I wasn't on campus today, because I really wanted to show you partial fraction decomposition in person, because it's one of my favorite sections, and I get a little nerdy about it. So I'll try not to make the video too long. I'll try to keep it on task. Thank you for your continued patience. I'll get to my email, I promise. I am looking at course messages on Blackboard way quicker than I am email, though. Have a great day. Stick with me. I got some things coming down the line for next week.